In section 5.6, we're going to look at indeterminate forms and L'Hopital's rule. We recall from earlier in the class, namely in chapters 2 and 4, that forms of the type 0 divided by 0, or some type of infinity divided by another type of infinity, are referred to as indeterminate forms because they do not guarantee that a limit exists, nor do they indicate what the limit is should one happen to exist. When we encountered one of these indeterminate forms early in the class, we attempted to rewrite the expression by using various algebraic techniques, things like factoring and canceling common factors, rationalizing numerators or denominators, or even simplifying complex fractions. In this section, we will discover a new analytic technique for finding limits of certain types of indeterminate forms, and this analytic technique we're going to talk about is what's referred to as L'Hopital's rule. This is theorem 5.18. Let's let f and g be functions that are differentiable on an open interval a to b, containing c, with the exception of possibly at c itself. Assume that the derivative of g is not equal to 0 for all x in the interval a to b, again with possibly the exception at c itself. If the limit of f divided by g as x approaches c produces the indeterminate form 0 divided by 0, then it's true that the limit as x approaches to c of f divided by g is actually equal to the limit as x approaches to c of the derivative of f divided by the derivative of g, provided the limit on the right hand side exists. So for the indeterminate form 0 divided by 0, we can take the derivative of the numerator, derivative of the denominator, and then see if we can find the limit that way. L'Hopital's rule also applies to the indeterminate forms of the type some type of infinity, whether it's plus or minus infinity, divided by plus or minus infinity. Okay. For example, let's see if we can evaluate the limit as x approaches to 0 of e to the 2x divided by x. As x approaches to 0, notice that the numerator would approach e to the 0, the denominator would approach 0, so this is going to be e to the 0 is 1 divided by 0, which is not an indeterminate form. So we've got to be really careful here. Remember, non-zero over 0 is going to give us an infinite limit. So this is going to imply that this limit is going to be an infinite limit. Let's investigate on either side of 0. Let's look at the one-sided limits. What would be the limit as x approaches 0 from the left of e to the 2x divided by x, and also the limit as x approaches 0 from the right of e to the 2x over x. In order to do this, you can do a table of values or look at the graph. But as x approaches to 0 from the left, that would be approaching to x from negative values. The numerator is approaching 1, which is positive, but the denominator would be approaching 0 through negative values. And if you take positive 1 and divide it by smaller and smaller negative values, the result is larger and larger negative values, which would be equal to negative infinity. Conversely, if we look at what happens as x approaches 0 from the right-hand side, now the denominator is approaching 0 through positive values, while the numerator is approaching positive 1. Positive 1 divided by smaller and smaller positive values will produce larger and larger values, so the limit from the right will approach positive infinity. So altogether, this limit, as x approaches to 0 in general, does not exist. Okay? So again, be very careful. This would not be something we could apply L'Hopital's rule to, because we didn't get an indeterminate form of the type 0 over 0, nor did we get an indeterminate form of the type some infinity over another infinity. This was a non-zero number over 0, which we know generally produces a infinite limit. Let's take a look at example 2. We want to evaluate the limit as x approaches infinity of the ln of x divided by x. As x approaches infinity, the numerator is going to approach infinity. The denominator is also going to approach infinity, and so we do in fact get an indeterminate form on this. So this is something that we can apply L'Hopital's rule to. So this would be equal to, by L'Hopital, the limit as x approaches infinity of the derivative of the numerator. The derivative of the ln of x is 1 over x, divided by the derivative of the denominator. The derivative of x is 1. So this is going to be equal to the limit as x approaches infinity. 1 over x divided by 1 is just 1 over x. And now as x approaches infinity, 1 divided by x is going to approach 0. So we found the limit here. Using L'Hopital's rule, the limit was equal to 0. Let's try another one of these. Let's take a look at the limit as x approaches negative infinity of e to the negative x divided by x squared. As x approaches negative infinity, x squared is going to approach negative infinity. And as x approaches negative infinity, did I say negative infinity? Positive infinity. X squared goes to positive infinity as x goes toward negative infinity. E to the negative x was also going to approach positive infinity as x approaches negative infinity. So for this is going to be another indeterminate form. So we can use L'Hopital's rule on this. So this is going to be equal to, by L'Hopital's rule, it's going to be the limit as x approaches negative infinity of the derivative of the numerator, which is 2x, divided by the derivative of the denominator. That's going to be e to the negative x. And then from the chain rule, we need to multiply by the derivative of negative x, which would be negative 1. As x approaches negative infinity now, the numerator is going to approach negative infinity. The denominator is also going to approach negative infinity. And so once again, we have another indeterminate form. That means we can use L'Hopital's rule again. This is going to be equal to the limit as x approaches negative infinity. The derivative of the numerator, well, the derivative of 2x is 2. The derivative of negative e to the negative x is going to be positive e to the negative x. And now as x approaches negative infinity, the numerator is a constant of 2. The denominator is going to approach positive infinity. And therefore, this whole thing is going to approach 0. So the limit in example 3 is going to be equal to 0. This example also illustrates that sometimes when we're able to apply L'Hopital's rule, we may often have to use that rule multiple times in order to evaluate the limit ultimately. Let's take a look at example 4. We're asked to find the limit as x approaches infinity of this e to the negative x times the square root of x. Initially, we would end up with something like this. As x approaches infinity, e to the negative x is going to approach 0, while the square root of x is going to approach infinity. 0 times infinity is an indeterminate form, but it's not a form that we can apply L'Hopital's rule to. Instead, let's rewrite this. And the way that we're going to rewrite it is by getting rid of that negative power of e by taking a reciprocal. We know that e to the negative x is the same thing as 1 over e to the x. So these expressions are equivalent. And now as x approaches infinity, the numerator approaches infinity. The denominator also approaches infinity. So this is a form to which we can apply L'Hopital's rule, because we ended up with the indeterminate form infinity over infinity. So via L'Hopital's rule, we would get the following. This is going to be the limit as x approaches infinity. The derivative of the numerator, we've seen that a lot this semester, so I'm going to skip that step. But the derivative of the square root of x, if you work it out and simplify it, should be 1 divided by 2 square roots of x. The derivative of the denominator, derivative of e to the x, is just e to the x. We want to simplify this complex fraction, keep, change, flip. This is going to be 1 divided by, it's going to be 2 e to the x squared of x. And now, as x approaches infinity, the numerator is a constant of 1. 2e to the x squared root of x, that quantity is going to approach positive infinity, and then 1 divided by larger and larger values is going to get smaller and smaller, and so we would see that the limit's going to be equal to 0. Some other types of indeterminate forms that do exist would be things like 1 to an infinity, infinity to the 0 power, and also 0 to the 0 power, arise from limits of functions that have variable bases and variable exponents. When we previously encountered this type of a function, we used logarithmic differentiation to find the derivative. We can use a similar procedure when taking limits, as we will now see in the next example.